Alright, so this is last problem dealing with electric forces, and then we're going to talk about another concept called the electric field. But for now, we're going to finish this problem here, and then I'll give you a couple ideas for ways you can practice different variations of this problem, because this is a pretty common problem dealing with Coulomb's law. So this is a situation where we only have electric forces in the problem, right? We're not dealing with like gravity or tension or anything like that. So we've got three charged particles, and they're all situated at corners of an equilateral triangle. So equilateral triangle means all three sides are equal. So all three of these lengths are 0.5 meters. An equilateral triangle is also equiangular, so this is 60, this is 60, that's 60 degrees. So that'll come in handy for later problems. So it says calculate the total electric force on the charge located at the origin. So we've got two positive charges. We've got a 2 microcoulomb, okay, that's mu for micro, that's 10 to the negative 6. So I talked about, we've seen nanocoulombs, we're going to see microcoulombs, so make sure you're comfortable with different orders of magnitude of charge. So the charge at the origin is a 2 microcoulomb charge, and it's going to experience a force due to both the 7 microcoulomb charge and the negative 4 microcoulomb charge. So we have to calculate the total electric force on the 2 microcoulomb charge. So since force is a vector, we're going to be dealing with both magnitude and direction. So the problem doesn't specify magnitude or direction, but I'm going to find the components and then find the magnitude and direction, just so I cover all my bases. If they're not specifying what format they want, I'm just going to go ahead and get both the components, x and y components, and then find the magnitude and direction. So the first thing I like to do is draw a free body diagram for the 2 microcoulomb charge, identifying the forces on it by the positive 7 microcoulomb and the negative 4 microcoulomb. So this is my 2 microcoulomb charge, and the force by the 7 microcoulomb charge on the 2 microcoulomb charge is in that direction. Okay, it's a repulsive force. These are like charges, so the 7 microcoulomb charge is going to apply a force that way. Okay, kind of like third quadrant, right? It's going to be a repulsive force. But the negative 4 microcoulomb charge is going to attract the 2 microcoulomb charge towards it. So the force by the 4 microcoulomb charge is in the positive x direction. So again, no other forces, just electric forces, but one of the forces is acting in 2 dimensions. So we're going to have to write Newton's second law in the x direction and Newton's second law in the y direction. So my net force in the x direction is the force due to the negative 4 microcoulomb charge. That's just in the x direction, so I don't have to resolve that. It's in the positive x direction, so it's positive. And in the negative x direction, you've got the x component of this force. Okay, you get the x component of this force. We got to go back to our skills we acquired from 120, resolve this vector into its x and y components. So this is the hypotenuse, right? This would be the opposite side, the y component, and this would be the adjacent side, or the horizontal component of that vector. So the x component of this force is its magnitude times the cosine of 60. Okay, so the x component of the force by the 7 microcoulomb charge is in the negative x direction, and it's the magnitude times the cosine of 60. How did I get this 60? So if I were to complete this triangle, right, the triangle where the charges are, this angle right here would be 60 degrees, right? They marked this angle as 60. So I took the x-axis and I extended it, and then when I drew this, the force vector from the 7 microcoulomb charge, I got a pair of vertical angles. Okay, so this angle is 60, and its vertical angle is right here. and vertical angles are congruent. Okay, so that's how I found out that this angle was 60 degrees right here. So we still got, you know, geometry and trig coming back to haunt us every now and again. So those are vertical angles, they're congruent. Alright, so 60 degrees. Now in the y direction, the only force that's acting in the y direction is this one. So I just have to take the vertical component of this force, which is the magnitude times sine of 60. Now it's acting in the negative y direction, so I have to give that a negative sign. Okay. So F7 on 2 is acting in both the negative x and the negative y direction, hence the negative signs. So I don't actually have to find like acceleration, so I'm not really using Newton's second law in its true form. I'm just adding up the forces in the x direction, adding up the forces in the y direction. So these are Coulomb's law forces. These are my expressions for the magnitude of these two forces. So I have the value of the charges, and I know the distance between the charges. I know my electrostatic constant, so both of these can be calculated. And both of these charges are 0.5 meters away, right? So it's the same distance between charges. So this distance is 0.5 meters, and this distance is 0.5 meters. So that's good, makes our lives a little bit easier here. So F net in the x direction is the force due to the 4 microcoulomb charge minus the force due to the 7 microcoulomb charge times the cosine of 60. So I have everything there. You know, I could plug my numbers in, but I do have some common factors just to kind of help with my calculations. Both of these terms have a k in them, both of them have q2 in them, and both of them have r squared in the denominator. So I'm factoring out a k, I'm factoring out the magnitude of q2, and I'm factoring out the r squared. And what I'm left with once I factor that out is the magnitude of q4 minus the magnitude of q7 times the cosine of 60. Again, factoring it out just to kind of, you know, not deal with powers of 10 as much as I have to, and kind of eliminate as many calc errors as I can. So I plug in my value for my constant, I plug in the magnitude of the 2 microcoulomb charge. Right? Again, the 4 microcoulomb charge is negative, but we're just talking about magnitudes here. Half a meter squared, right, for r squared, and then plug in the magnitude of the 4 microcoulomb charge, magnitude of the 7 microcoulomb charge. So once I calculate this value, I get a very small force, 3.6 times 10 to the negative 2 newtons. So that's what we're going to be dealing with as far as the, you know, the magnitude of forces. They're going to be very small between charges that are, you know, on the order of microcoulombs or nanocoulombs. They're going to be very, very small forces. So 3.6 times 10 to the negative 2 newtons, that's in the x direction. So I've got the x component, I'm ready to calculate the y component. So I've got k, I've got the magnitude of the two charges, the same distance, right, half a meter squared, and now I'm using sine of 60 because it's the y component, and it's negative, so I can't forget to bring my negative sign along with me, and I get 4.4 times 10 to the negative 1 newtons. So that's, you know, a little over 10 times more than the force in the x direction. That's because the force in the y direction is just due to the 7 microcoulomb charge. The force in the x direction is a combination of the force due to this charge and the force due to that charge, which is acting in the opposite direction. So we've got a much larger force in the y direction than we do the x direction, which is okay. It makes sense based on, you know, the configuration. So now I'm going to use my Pythagorean theorem thing here to calculate the magnitude, right? The magnitude of the forces. My x component, actually I think I got them switched, but addition's commutative, so we're okay. So the x component is this one, the y component's this one. So I calculate that, and I've got a new magnitude of 5.7 times 10 to the negative 1 newtons. So that's the magnitude. I've got the components, right? So again, they didn't specify what form they wanted the force in, so I'm taking care of all of that just in case. So the magnitude is 5.7 times 10 to the negative 1 newtons. I want the direction too. So I'm taking the inverse tangent of the y component over the x component, right? So I got a negative y component, a positive y component. Your calculator's probably going to give you a negative sign, right? So in 120 we kind of talked about how to interpret that. So what I do is I always draw a picture of the vector because I want to describe the direction, right? I don't just want to throw an angle there and leave it up to somebody else to interpret what that means. So I get 85 degrees, but I get a negative sign. Now what this means is your calculator doesn't know whether you're dealing with a fourth quadrant vector, negative y positive x, or a second quadrant vector, positive y negative x. It just knows that this number is negative, right? So I disregard the negative sign and then I draw a picture of my net force vector, at least its direction, right? It's got a negative y component, a positive x component. So I'm in the fourth quadrant. This angle theta, this reference angle, is being measured from the positive x-axis. Okay, so I'm going to say it's 85 degrees below the positive x-axis. Right? I always want to measure from the nearest x-axis. That's my convention, because that's how I like all my right triangles to look. Because the x component stays with, you know, the cosine. Y component stays with the sine. I don't have to mess with my formulas, anything like that. So I've got the magnitude of the net force, and I've got the direction of the net force. Okay, so next topic, okay, is what's called the electric field. Now what I'm going to do is I'm going to go back to gravity for a bit. Okay, go back to gravity. In 120 we dealt with gravity, and it looked like this, right? The mass of an object times the acceleration due to gravity. Now near the surface of the Earth, it's roughly 9.8 meters per second squared, right? We just use that for lowercase g. Newton's universal law of gravitation states, this is for any case, right? Any distance between planets, right? Planets, stars, satellites, whatever. So it's proportional to the product of the two masses, right? If let's say we take the Earth-Moon system, right? We'll say capital M is the Earth and lowercase m is the Moon, right? And r is the distance between those two objects. So it looks a lot like Coulomb's law, right? Directly proportional to the product of the masses, inversely proportional to the square of the distance between them. So this is a force. This is in newtons. Newton's gravitational constant has units that will cancel out the meter squared, cancel out the kilogram squared, and you'll be left with newtons. So if I take this, right, our original form of the gravitational force, and I solve it for g, I get g, right? And I know what it is near the surface of the Earth, 9.8 meters per second squared. Lowercase g we calculated based on Newton's law of universal gravitation, and I'll show you where that comes from. But I look at these units, and they're also in units of newtons per kilogram. So an acceleration is a unit of force, or is in units of force per unit mass, right? So what does that mean? If I had a 1 kilogram mass near the surface of the Earth, it would experience a force of 9.8 newtons. Okay, so it's kind of like a ratio, right? It's a force to mass ratio, right? How much force would an object of a certain mass in that region feel due to the gravitational field of the Earth? And that's the point I'm trying to get to now, is that it's a gravitational field. Okay, this exists near the surface of the Earth, whether you picked a ball off of the floor and dropped it or not, right? If you've got an object in space near the surface of the Earth, it's going to feel this force due to gravity. But if that object wasn't there, this field would still be there, right? This field would still be there. And so that's kind of the point of this new concept of electric field, right? So if I take, here's what I did. If I take the force by Newton's law of universal gravitation, right? If I take this expression as the gravitational force, right, for any distance from the surface of the Earth, and I substitute that in here, what happens is, and again we're going back to like the Earth-Moon system, if I plug that in, the mass of the moon goes away. Right? The mass of the moon goes away, and so I have my gravitational constant, I have the mass of the Earth, and I have the distance between the Earth and some location where the moon is. I'm still in newtons per kilogram, it's a gravitational field, but the value of this gravitational field only depends on the mass of Earth. See, it's independent of the mass of the moon. Right? So I'm just calculating the value of the gravitational field at this location. Okay, so there's still a field there. Even if the moon wasn't in orbit and it wasn't under the influence of gravity, I could still calculate the magnitude of the gravitational field at that location. And so the same thing applies for electric charges. We've been dealing with two interacting charges, right? Maybe one's positive, maybe one's negative, you know, maybe they're both the same charge, whatever. So they've always been two interacting charges. But if I take one of those charges and I identify it as, let's say, the source charge, right? Let's say this is our planet Earth analogy, right? And this test charge is our moon, right? If this thing went away, if this Q naught went away, there would still be a field here. And we're going to call that field capital E, right? Capital E. And this electric field, in this case, it's going to point away, right? It's going to point away from this source charge. So what this means is, if we put a positive test charge at this location, it would feel a repulsive force. So that's how we're going to define the electric field. The electric field is going to point in the direction that a positive test charge would travel if it was placed at that location, right? So if we had a negative source charge and we put a positive test charge at some location, the electric field would be pointing towards the negative charge, right? If we put a test charge at the same location but our source charge was positive, the electric field would be pointing away. So the electric field points in the same direction that a positive charge would feel if it was at that location. But we're dealing with no charge there, right? That's just we're just calculating the field at that location, regardless of what charge may be there. And so our definition, you'll see that it looks very similar to this, my gravitational field, right? Force per unit mass, but instead of force per unit mass, we're going to say for an electric field, it's force per unit charge, right? Force per unit charge, that's my test charge, right? And just for simplicity, that could be a 1 coulomb test charge, okay? So these are units of newtons per coulomb, right? Our gravitational field was newtons per kilogram. This is a ratio, force per unit charge, okay? So newtons per coulomb is my electric field units. And similarly, I take the force, the Coulomb's law force, I divide it by Q naught, like I did here, right? Divided it by the mass of the moon, or the mass of my test mass, whatever was at that location. So I divide both sides, or I divide both sides by Q naught, and I get F over Q naught, which is equal to E. So now I've got an expression that I can use to calculate the magnitude of the electric field at any location. So this thing is gone, right? I threw this charge away, it's not here anymore, but I still have this source charge. So if I picked a point, some distance r from this source charge, I can use this expression and calculate the electric field. The magnitude, at least, right? I have to use this, a positive test charge, to determine the direction, right? It always goes away from the positive source charge, right? Because the electric field points in the direction that a positive charge would be accelerated. So the electric field's always going to point away from a positive test charge, and it's going to point towards a negative test charge. So that's my electric field. So I can calculate the electric field of one singular point charge or multiple point charges in space. So these are what we call our field diagrams, right? The electric field is a vector field, much like the gravitational field. If you look at this one, right, if I were to draw the gravitational field of Earth, it would look very similar to this, right? Because everything with mass is going to get pulled towards the center. But the farther I get away, the weaker the field is, right? Because it's an inverse square law. Okay, so r squared is in the denominator of my electric field term. So the farther away I am from my charges, the weaker the field gets. And again, it's always pointing away from a positive charge, because if you put a positive charge here, it would go in that direction. And it points towards a negative charge, because if I put a positive charge here, it would be attracted. Okay. But again, it's an inverse square law, so the farther away you are from a charge, the weaker the field is. So let's do an electric field calculation. So we've got 3-point charges. I don't see any negative signs, so I'm going to assume they're all positive charges. They don't have negative signs on the charge or anything like that. So I've got 3 charges. Remember that electric field is a vector, so we're still going to have to split it up into its x and y components, find the magnitude, direction, all that stuff. All right. So I'm calculating the electric field in the top left corner of the rectangle. So the first thing I'm going to do, I'm going to look at all 3 of these charges, and I'm going to see what is the direction of the electric field due to those individual charges. They're all positive. So if I'm right here in the top left of the rectangle, the field due to the 3 nanocoulomb charge is going to be in the positive y direction. Remember, away from positive towards negative. So the field due to the 3 is in the positive y direction. The field due to the 6 is going to be in the negative x direction. Okay, positive source charge. If there was a positive test charge here, it would be in the negative x direction. Now I still have this 5 nanocoulomb charge, so it's going to be acting at an angle, right? See how it goes across the diagonal of this rectangle? So it's going to be like a second quadrant vector. Right? It's going to have a positive y component and a negative x component. Right? So the 3 and the 6, I don't have to split them up because they're acting in the y and the x direction respectively. But the 5 nanocoulomb charges field is a 2-dimensional vector, so I have to resolve that. So I do kind of like a free body diagram, right? I can do a free body diagram even though I'm not dealing with forces. So it's just a vector diagram identifying the direction of these 3 electric field vectors. Again, E3 is in the positive y, E6 is in the negative x, and E5 is in the positive y and the negative x direction. So I got some things missing, right? I got a theta here. There's something else that's going to be missing as we set this problem up. So I'm looking for the net electric field. We write E net in the x direction. So E net in the x direction is E6 in the negative x direction, negative sign, minus E5 cosine theta. Again, I like this angle with respect to the nearest x-axis. So E5 cosine theta is my x direction, my x component of my E5 vector. E net in the y direction is E3, positive E3. It's just in the y direction, plus the y component of E5. So it's positive E5 sine theta. So I use my electric field. This is one of the most common mistakes I see. We get an electric field problem and then we treat it like a Coulomb's law problem. Alright, but there's not a charge there. Right? There's not a charge there at that point, so I'm just calculating the electric field. So don't confuse your Coulomb's law force expression with your electric field expression. So the field due to the 6 nanocoulomb charge is K times the magnitude of Q6 divided by r squared. Now what's this r? This r is the distance between the 6 nanocoulomb charge and the top left corner. And that is 0.6 meters. So the distance between the 6 nanocoulomb charge and the top left corner is 0.6 meters. Right. So E3, the electric field due to the 3 nanocoulomb charge, is K times the magnitude of the 3 nanocoulomb charge divided by the distance between the 3 nanocoulomb charge and the top left corner, which I see The rectangle is marked nicely for me, 0.2 meters. What about the distance between the 5 nanocoulomb charge and the top left corner? So it's the diagonal of a rectangle. Half of a rectangle is a right triangle. So I have one side of the right triangle, 0.6 meters. I've got the other side of the triangle, 0.2 meters. So I'm looking for the diagonal of the rectangle, which is just the hypotenuse of that right triangle. So 0.6 meters squared plus 0.2 meters squared, take the square root of that, and I've got 0.63 meters. Okay. Now don't forget, I'm going to have to square that again. So really, technically, I could have just left this as R5 squared and not taken the square root of this side. But I'm going to plug 0.63 meters in here and then square it again. So I've got my distances, I've got my charges, so I can calculate the magnitudes of these three charges. But before I do any calculations, I'm just going to substitute the expressions in and then wait till the last minute to wait till the last step to plug my values in and calculate. So E net in the x direction is negative E6 minus E5 cosine theta. So negative E6 minus E5 cosine theta. Now I could factor out a k. You know, you don't really have to, because there's not a whole lot to factor out. It doesn't make my life that much easier, but I factored out a k, and I factored out a negative sign too. See how both these terms are negative? So I factored out a negative k. I'm left with q6 over r squared for the 6 nanocoulomb charge, 0.6, plus q5 over the distance that I found up here, right, the diagonal of the rectangle, 0.63 meters squared, times the cosine of that angle. Now where is that theta? Where is that theta? So I've got this right triangle, right? I know the hypotenuse is 0.63 meters, but I also know the adjacent and the opposite side, right? The opposite side of the right triangle is 0.2 meters, adjacent side is 0.6 meters, so I can use the inverse tangent of the ratio of these two sides to find that angle. Okay, so that's the angle I'm looking for, the angle that the E5 vector makes with the negative x-axis. So inverse tangent of 0.2 over 0.6, I get 18.4 degrees. So that is my reference angle when I'm resolving the E5 vector into its two components. Okay. Electric field is still a vector, so we still got to do all that vector mathematics, the same thing we did with forces. So I calculate E net in the x direction. I get a negative 257.6 newtons per coulomb. Now we're getting small forces, but I'm getting large electric fields, because remember, electric field is a ratio newtons per coulomb, so it's a force per unit charge, and a coulomb is actually a very, very large amount of charge, and we're usually dealing with much smaller charges than that. So even though we get large electric fields, don't be alarmed, because the charges we usually put in that location are much smaller. So E net in the y direction is E3 plus E5 sine theta. So again, I'm just adding up those two E field vectors in the y direction. I've got k, I've got q3 divided by 0.2 meters squared, the distance between the 3 nanocoulomb charge in the top left corner, plus q5 over that distance again, the 0.63 meters, times the sine of 18.4, because it's the y component of E5. So I get 710.7 newtons per coulomb for the net electric field in the y direction. Use the Pythagorean theorem, find the magnitude of the net E field, and I get 756 newtons per coulomb. Use the inverse tangent of the y component over the x component. So I've got a positive y component and a negative x component. That tells me I'm a second quadrant vector, right? Positive y, negative x. So I draw that vector, right, in the second quadrant. X component is negative, y component is positive. This is the angle I'm looking for. The angle measured from the nearest x-axis. That's what I like. That's because it's the easiest way for me to describe it. So I get 70.1 degrees, and that angle is measured above the negative x-axis. Okay, 70.1 degrees above the negative x-axis. So we're dealing with electric field vectors just like we dealt with the Coulomb's law of force vectors. The same thing we did in 120 when we were dealing with velocity vectors and momentum vectors, all that stuff. Okay, so electric field is a vector. Even though there's not an actual charge there at that location, there's still a field based on these three charges, the fields that these three charges generate at this location. Alright, one more electric field problem. So there's a hard way of doing this, and then there's an easy way of doing this. I like to do it the easy way. And the reason I like to do this is because I like to eliminate as much vector mathematics stuff as I can. So if you notice, this is a square, and there are charges at all four corners. Now the charges are different in magnitude. I'm going to say they all look like they're positive. Again, I don't see any negative signs. I get a value for Q, right? And I'm very tempted to say, alright, this is 5 nanocoulombs, this is 10 nanocoulombs, 10 nanocoulombs, 15 nanocoulombs, right? And I know the value of the sides, right? They're all 0.1 meters. But I'm going to start this problem just by dealing with the variables, right? Before I start plugging in numbers, because I don't want to, I don't want to mess my process up with numbers, however nice they may be. So we want to know the electric field at the center of the square. So what's happening physically is this Q is going to generate a field in the third quadrant, say, right? It's going to push some charge down that way. The 2Q is going to push a charge down that way. This 2Q is going to push this charge up that way, and the 3Q is going to push a charge up that way. Right, so there are 4 different electric fields here, right, all pointing in opposite directions, and they're all in 2 dimensions, right? They're all in the X and Y direction. I'm going to have to resolve 4 different forces, right? That's crazy. And then angles and distances and all that crazy stuff. So I'm looking for a way to simplify this problem so I don't have to resolve as many vectors. So here's what I did. So this is my sketch of the square, right? I got my Q, I got my 2 Q's here, and I got my 3Q, right? And I've got the lengths, right? A. First thing I'm going to do is I'm going to look at all these charges, and I see that they're all scalar multiples of one another, right? Q is 5 nanocoulombs, right? But this is twice that. This is twice that. This is 3 times that. So when I draw E field vectors here at the center due to all 4 of these charges, here's what I notice. I've got E due to the 3Q in that direction, E due to the Q in that direction. And then along this line, I've got 2 E fields due to like charges, right? So the field due to this charge is actually going to cancel out the field due to this charge. They're equal in magnitude, okay? They're opposite in direction. Charges are the same, okay? And they're both the same distance from the center, right? This is the center of the square, so they're both the same distance. So what I recognize to make my life easier, I get rid of 2 E field vectors because these 2 electric fields, due to these charges, are going to cancel each other out. So I can ignore them completely. That's very nice. Now I only have to deal with the E field due to the 3Q, and then the E due to the Q. Again, Q is the same. All of these charges are the same distance from the center. So this is actually just 3 times this electric field. If you notice, they're the same distance, right? Q is the same. This electric field due to the 3Q charge is 3 times the strength of the electric field due to the 1Q charge. So if I were to add up these 2 vectors without doing any type of algebra or anything like that, or substituting any values, I see that the net electric field along this line is the sum of these 2 vectors, E3Q minus EQ, which is just E2Q. So my net electric field at the center I can rewrite as just E sub 2q in the positive x and the positive y direction, right? So these two E fields are canceling each other out. This one is 3 times as strong as this one. So this minus that is just E2q. So that saves me a lot of work. Now I only have to deal with the electric field due to one 2q charge in the bottom left corner of the square. So let's say I want to find this magnitude, right? I'll deal with the direction later. That's a geometry thing. So I'll deal with that direction later. I'm going to find the magnitude first. Okay. So I know what K is. I know what Q is. It's 5 nanocoulombs. So I'll be ready to substitute that. What's the distance between one of the corners of the square, in particular the bottom left corner, and the center? So what I did was I took this square and I drew 2 diagonals through it, and I split it up into 4 right isosceles triangles. Okay, so each one of these 4 triangles here, and I have this one starred, each one of these 4 triangles is a 45, 45, 90 triangle. Okay, now I know from geometry, I spent some time teaching geometry, so it's a little fresh in my head. But if it wasn't for that, I wouldn't recognize this this property. Okay, this is an x root 2 triangle. All right, that's the ratio of sides of a right isosceles triangle. I'm looking for this distance. I'm calling it x. Okay. Excuse me. If you don't recognize that it's x root 2, or you don't recognize like some other ratio of a 45, 45, 90 in here to get an expression for x, you can always use the Pythagorean theorem. These two sides are the same, so x squared plus x squared is a squared. Okay, so I'm using the Pythagorean theorem. If I add these two x squareds up, I get 2x squared. Now, if I solve that for x, I would divide both sides by 2 and take the square root of both sides, and I get an expression for x, which is a root 2 over 2. Okay, and actually that's like some unit circle stuff there too, right? The sine of 45 is root 2 over 2. The cosine of 45 is root 2 over 2. So you can look at it from a trig perspective as well. But when in doubt, you can always use the Pythagorean theorem. But I know it's an x root 2 triangle, 45, 45, 90. So I can calculate what x is, but I'm just going to use this expression, and then I'll plug in 0.1 meters for a later. So I plug in a root 2 over 2 for x. That's the distance between one corner of the square and the center. So let's see, if I square this, right, I get a squared, and then that becomes a 2, and that becomes a 4. Okay, so q I'm not plugging in yet, a I'm not plugging in yet. So I squared a, this root 2 squared and this 2 cancel. Okay, so those 2's go away. This 4 is in the denominator of the denominator, right? So I got to do my reciprocal multiplication thing, and that comes up to the numerator. So my simplified expression for this electric field is 4kq divided by a squared. So I do all this algebra with my variables and my coefficients and stuff before I start plugging in my super big and my super small numbers. Okay, so I have 4 times k, 9 times 10 to the 9 Newton meter squared per coulomb squared, times q, which they told me was 5 nanocoulombs, 5 times 10 to the negative 9 coulombs, divided by a squared, 0.1 meters squared. And I get a magnitude of 2,450 newtons per coulomb. So I saved myself a lot of work by recognizing the proportions of the electric fields at that point, and so I could reduce it to one electric field because of that property. Now I want the direction. This was calculating the magnitude. I want the direction, okay, and since it's acting from the corner of a square, it's acting equally in the x and the y direction. right? So it's in that direction. It's acting along the diagonal of the square. So the angle that this makes with the positive x-axis is just 45 degrees. 45 degrees above the positive x-axis. So there was a lot of nice symmetry. It's a very nice shape. And so just recognizing some geometry and trig properties helped me to simplify this problem. So for practice, go back and maybe make one of these negative, right? Or go back to this problem and make the 5 nanocoulomb negative, or make the 6 nanocoulomb negative, right? Change the direction of an electric field and then see how that changes the net field due to a negative charge being in that configuration. Another practice problem you could do, a lot of these, right, problems deal with this charge here at the origin, right? So some practice, you can calculate the net force on the 7 microcoulomb charge due to the 2 and the negative 4, and then you could go back here and find the net force on the negative 4 microcoulomb charge due to the 7 and the 2. Okay, and take one away, right? Take the 7 microcoulomb charge away, and then calculate the field due to these two charges, right? So you can take these, these diagrams. There aren't a whole lot of them out there, so you can take these diagrams and take a charge out and calculate the field there, or switch the charges around, or switch the signs of the charges, and that'll give you some good extra practice. Obviously, the WebAssign, those are good examples. Some of them can be a bit more challenging. They might take a little more time to think. Plus, they don't use very nice numbers, which can be annoying. But always practice good problem-solving skills as far as get an expression for what you're looking for first before you start plugging numbers in. Right? I know we like to plug numbers in because it's stuff we know, it's stuff that the problem gives us, and it kind of makes us feel better as we're solving the problem. But I find that it's much easier to avoid calculation errors if you solve the problem in terms of all the variables and then wait till the last step to substitute those values in. So try and practice that as you're doing the WebAssign, or you're practicing these extra problems in here. Any questions, let me know. Syllabus is on D2L under the overview tab in the content section. I also sent you an email. I have office hours from Monday through Friday. I believe it's noon to 1. So I don't have a default Zoom meeting scheduled. Okay, so if you want to see me, you're more than welcome to talk via email if you're more comfortable with that. If you want to Zoom, just let me know. Just let me know when you want to see me during office hours. Just send me an email, and I'll send you a Zoom link, and then we can Zoom that way. Also, if you want to meet another time other than 12, let me know. What I'm doing right now is basically what I do throughout the day, with the exception of planning out curriculum and making assessments and grading assessments and stuff like that. So I'm home pretty much all the time. So if you need to meet at 10 a.m. or 2 p.m. or something like that, send me an email. Be more than happy to Zoom with you. Share my screen, talk as best as we can through Zoom, or email. Email is always good. So feel free to get in touch with me, and I will get started on chapter 16 in a little bit. All right, thanks.